Well, greetings out there in YouTube land, and welcome to today's big video featuring the contents of this recently delivered box. We have our fresh Depends to put on before opening, just in case the contents are sort of overwhelming to our digestive system. Okay, so without further ado, no pun intended, let's cut open the box and see what has been sent to us for repair. Looks like another beautiful packing job. Nice thick foam over and all the way around the amplifier. Folded up paper for protection. It looks like an absolutely first-class job. So let's go ahead and get that amp out of the box and see what our challenge is. Well, lo and behold, we have before us here an absolutely magnificent, I believe 1967 blackface Fender Princeton Reverb amp in just stunning original condition, beautifully cosmetically preserved. We see here some very obvious electrolytic capacitor changes using discrete capacitors rather than a single can cap. See the oversized 470 ohm screen resistors. Use of clear insulated wire, sort of some modern looking components that jar the eye, which no doubt work well, but let's read the letter and see what the owner of this amp wants us to do for him. And here's the letter. 67 blackface Princeton Reverb functions properly in its current state. Restore it to its original condition by reversing the Pentode Triode modification and installing the proper filter cap can. He wants the NFB to remain switchable, but move the switch to the ground switch position after the Triode Pentode switch is removed. Replace the power cord. It was found to be in good health by some previous tech. Once the tremolo slowed down, and finally, and this will be more challenging, it's something we're going to have to think about. Current tone has, in his opinion, excessive mid-range, and he wants this to have the mid-range scoop that he associates with most blackface amps. Okay, we're going to have to check into that. That's going to be sort of a subjective modification, but all this stuff's very straightforward. So with that in mind, let's take a good look at the amp chassis to see what we're beginning with, and then order some parts and get started. As already noted, the control panel is a little dusty, but essentially flawless. I'm going to go slowly over the circuit. As previously noted, a lot of electrolytic changes, and these 20 years ago were probably just fine as far as capacitors go, but now we tend to use a little bit higher quality caps. I do, at least. Not much else seems to be modified. Looks like the cathode bypass caps have been replaced, but these may well be acceptable. We'll see. Okay, these kind of stick out. The screen resistors, you see the switch here that is added for the Triode Pentode switching, and then we have an on-off. I think this is going to be the NFB switch that's been added in here. This then will be moved over here. This will be removed completely. Going to use some period correct wire. I have the exact type of wire that they used on black-faced Fenders. Okay, so as you can see, the rear control panel, other than those two switch modifications, appears fine. I see they removed the auxiliary outlet to make room for the NFB switch. Thank God they didn't drill a hole in the chassis, so I think what I'll do is try to hunt down a replacement receptacle to put back in that position, and then we will use the what used to be the polarity switch for our NFB. Everything else looks real straightforward. Let's take a look at the top of the chassis, or bottom, I guess, depending on whether you're in Australia or North America. And as we can see, it's clearly up to the standards of the rest of the amp. Magnificently original. We see here the reverb tank driving transformer. We've said in previous videos, what this amounts to is an output transformer for the reverb tank. You drive the reverb tank just the same as you would a speaker. So here's our output transformer for the speaker. Here's our output transformer for the reverb tank. We're going to have a 8 ohm impedance in the secondary of the reverb driver, and in the first transducer coil for the reverb. So we have an 8 ohm to 8 ohm impedance match in the reverb driver transformer and in the output transformer as it interacts with its speaker. Okay, so everything looks totally original and legit here. I'm just overjoyed. I'm thinking somebody drilled some holes. Ugh, that kind of upsets the old digestive system, and I'm glad I have my Depends handy. But we're going to get this out of here and put in a nice can cap, which may not have been available 20 years ago. Okay, so, but they are now, hopefully, with all the other shortages that we've been having lately. Hopefully that doesn't affect the availability of can caps, but that's something that I'll have to order. I just used my last one a month ago or so. Okay, so we're dealing then with a world-class, beautiful, original Princeton Reverb chassis, and we know what our assignment is, so let's get started. Step one, I've downloaded a AA764 Princeton Reverb amp schematic from the internet. People contact me all the time and ask if I have certain schematics. Well, I don't have like a library of ancient schematics. I just go to the internet and download them just like you have to. Okay, so sometimes it takes some looking. Fortunately, with Fender amps, it's not that hard. But the reason for this is when you have a highly molested circuit like this, who knows if they put in the right values. So if you go in and just duplicate their values in different positions, you might be duplicating an error. So it's best when you do have one like this that's been altered, that you have a schematic to show you the proper values. And here's a good example. Right here, the third internodal resistor is brown, green, that's a 15K. But you look over here on the schematic, it's supposed to be 18K. Now odds are they didn't have an 18K on hand, so they just put in the 15K and figured that was good enough. And it may well have been, but we're going to do it right. Okay, so now I'm going to make a list of all the parts that I have to order. Hopefully I'll be able to find the screw-in receptacle, the can capacitor, proper value carbon film resistors I'll use, and things of that sort, proper value caps, and I'm going to order all those parts, and then we can get started restoring this chassis back to a really nice original condition. I think step one here should be the removal of the NFB switch and the restoration of one of those vintage Amphenol 2-pole AC receptacles in this hole right here. Now these receptacles are very hard to get. I was looking on the internet and they're offered like at say $37 a piece, which seems outrageous to me. Now I happen to have the Amphenol AC receptacle here, but it doesn't have the flange or the retainer to hold it in place. But I did find in my surplus electronic gear a flange and retaining ring on a 6 prong plug. So I'm going to remove that retainer and flange and reinstall them on the Amphenol plug and see if we don't have a perfectly fine replacement for our missing receptacle. And there we have it. The flange and the retaining ring have been removed from our hex plug and now can be reinstalled on our Amphenol AC receptacle. And there you have the finished product ready to be installed in the chassis. I did the slots at a 45-degree angle because, as I recall, that's the way they are on the Fender amps. They're not straight across as you kind of would expect, but angled like that. So even that is carefully been done to fool all observers. So now we have our magnificently restored Amphenol AC receptacle ready to be installed in lieu of the incorrect NFB switch. Okay, I removed the 2 wires that went to the NFB switch, and I pushed out the plastic plug that was used to mount it. Now, after removing the stick-on labels, we can install the proper AC receptacle. Now we have the auxiliary receptacle installed in the chassis, and I'm anxious to move on to removing the Pentode Triode switch. Now some of you may be interested in adding this modification to your circuit, so let's take a few moments to discuss how the switch is wired and how it functions. Now, since the wiring in this area is rather congested, I thought it might be helpful to draw a diagram of how the switch is wired. I thought it might be helpful before our discussion begins to discuss how double pole, double throw toggle switches work. In effect, it's like 2 separate toggle switches. You have the upper set of contacts and the lower set of contacts. They're completely separated. Okay, so when the toggle is in the switch to the right side, the contact portion of the toggle is down here, and it will close these 2 contacts and these 2 contacts. And like I said, the upper and lower are completely separate. In the case of this switch, we will jumper them, but that's only for this circuit. Without that jumper, the upper and lower contacts are completely separate. Now when we flip the toggle over to the left side, the contact portion then will close these 2 contacts, and separately it will close these 2 contacts. Now keep that in mind when we continue our discussion. Next, let's talk about the wiring of a pentode, a tetrode, and a triode. In a pentode, pent meaning 5, there are 5 independent structures: the plate, suppressor grid, screen grid, signal grid, and cathode. In the tetrode, you will have the plate with the suppressor grid connected to the cathode. Okay, so now we have 4 independent structures within our tube: the plate, the cathode, the control grid, and the screen grid. Now in a triode, it's like a tetrode in which the suppressor grid is connected down here to the cathode, but to reduce it down to only 3 independent parts, we will jumper the plate to the screen grid. Okay, so now the independent parts within the triode are the plate, signal grid, and cathode. Now, what's the advantage of this? A pentode in an output tube will have more gain because we have these the suppressor grid and the screen grid functioning to improve the flow of electrons to the plate. In the tetrode, we'll have slightly less gain because we've eliminated the independent function of the suppressor grid, which is the upper one here. In the triode, we'll have the least amount of gain because we only have 3 independent functioning parts. We've eliminated the independent function of the suppressor grid and of the screen grid. Why do we do that? Well, in some of your real high dollar, hi-fi amplifiers, they'll have triode output tubes. These are generally very expensive, but you get a extreme purity of tone. You're sacrificing some gain for this ultimate purity. In most cases, we think of guitar amps as not having that extreme purity, and we'll go with our Pentode or perhaps Tetrode output tubes. So this switchability here, and it was a misnomer really to call it a Pentode triode switch. It's really more of a Tetrode triode switch because both the 6L6 and the 6V6 have internally connected the suppressor grid to the cathode. So that switch then would give us the choice of a full high gain guitar type output tone, or rather pure clean output tone. Now let's see how that's done and how we will wire the tubes to achieve this. Okay, before we start looking at some diagrams and discussing how that Pentode triode switch works, let's talk about a component that we see in this circuit which normally is not in a Princeton Reverb circuit. And that is those large 5-watt 470 ohm ballast resistors that were used as screen resistors in the circuit. Now normally Princeton Reverbs do not have screen resistors, and I'm going to explain to you why they don't and why this circuit has them. Screen grids are sort of a problematic structure in tubes, in that if you're going to have a short in a tube, odds are many times it involves a screen. Okay, so since they are prone to creating shorts, we have to take some precautions with our circuit to prevent that short from damaging our power transformer. And so in circuits that have filter chokes, and we'll see why in just a second, screen resistors are employed as sacrificial components. That means that they're in there to serve no other purpose than to fail if a short develops downstream. They're like fuses. Okay, if a short develops in the screen and a lot of current starts to flow, your screen resistors will overheat and fail and stop the flow of current to the short circuit. And in so doing, they will protect your power transformer, which, as you all know, is the most expensive single component in any amplifier circuit. Now, to see why screen resistors are essential in circuits that have filter chokes, let's look at a Deluxe Reverb schematic. We see here the high voltage winding with the B+ coming up here through the standby switch and on up through the primary of the output transformer and to the tube plates. So far so good. But our screen supply passes through the filter choke, which is right here, it's called TR2, and then proceeds up to be distributed to the two screen grids. Now the problem arises when there is a short in one, or Paris thought both of the screens. All sorts of current will be flowing up here to that short circuit, and the filter choke will not act as a sacrificial component. It can handle all sorts of current, and also it has a good heat dissipating capability, so the current's going to continue to flow up here to the shorts until the high voltage winding is fried, as well as your pocketbook when you buy a replacement power transformer. So Fender and other manufacturers wisely added screen resistors, 470 ohm, 1 watt screen resistors right here, to act as sacrificial components, or fuses if you will, in case of a screen short. So as the current comes raging up through the filter choke, the one or both of the screen resistors will overheat, fail, open the circuit, and protect your power transformer. Now let's see why the Princeton Reverb circuit does not need screen resistors. Okay, it wasn't a matter of economy, it was just a matter of common sense to exclude them from the circuit. And here's why. Here comes our B plus, rising up here, going to the two plates, and then our screen supply is going through not a filter choke, but a 1000 ohm 1 watt resistor, and then coming up here and it is distributed to the screens. This is the sacrificial component in case of a screen short. Okay, as you can see, the excess flow of current will greatly overpower the 1000 ohm resistor. It will burn and open and will protect our power transformer. So adding screen resistors to a Princeton Reverb circuit with a 1000 ohm internodal screen voltage dropping resistor is unnecessary and redundant. So we will remove them from this circuit simply because they're not needed and they're not original. Now why, you ask, did they put in screen resistors in our circuit? The reason is because of the Pentode Triode switch. Okay, and I will explain that in just a minute when we get to the triode position of that switch. For now though, let's focus at the Pentode position, see how the switch works. Before we start talking about the switching circuit, let's note that the plates of both of the output tubes have their own independent supply of B plus from the output transformer. Okay, nothing about the switching or the circuit that's added to make it a Pentode triode switchable circuit will affect that. The plates have their own dedicated B plus supply from the output transformer. Now let's look at the switch. We see that we've already discussed that when the switch is in the right hand position, the left hand contacts are closed, and the upper contacts here are closed, the bottom contacts are closed. Now what's happened is we bring in B plus from the power transformer, not the output transformer, but the power transformer, run it through the 1K internodal resistor that we discussed on the Princeton Reverb schematic just a few minutes ago. We bring it past that 1K sacrificial resistor, bring it up here, and we distribute it through the closed contacts down here to pin 6 of the output tubes. The upper contact supplies the pin 6 on the left hand tube, the lower contact supplies pin 6 on the right hand tube. Now pin 6 has no connection in the tube, okay, which is why you'll see NC here, no connection. Okay, it's like a terminal strip. We're going to use it just to attach our wire. Then we're going to run the 470 ohm screen resistor that you saw in the circuit when we looked it over closely, and run it between the no contact pin 6 and the screen, which is pin 4. Okay, and we're going to do that in each tube. Okay, so that now our screens will be receiving the B plus from the power transformer through the 1K internodal resistor. This is exactly like we saw in the schematic, with the addition of the 470 ohm screen resistors, and you'll see why when we get to the triode section, why the screen resistors have to be added even in the Pentode position. Let's look up here then and see why it really is a Pentode, or actually Tetrode, position for the toggle switch. We have the independent supply for the plate, and we have, this is from the output transformer, and then we have the high voltage winding from the power transformer providing the B plus for the screen. It's passing through the 1000 ohm internodal resistor, and in this case, because of this modification, a 470 ohm screen resistor. There is no direct connection between the plate and the screen.
Now by contrast, let's flip the toggle switch over to the triode position and close the right hand upper and lower contacts. Okay, all of this wiring is the same as it was up above, and that is that from this contact we'll come over here to pin 6 through a screen resistor to the screen. Here we come down here to pin 6 through the screen resistor to the screen. The difference is, instead of providing the B plus through the 1K internodal resistor, we're now going to apply the B plus directly from the plate. We see here that a wire comes up from the right hand plate to the bottom terminal. Over here it comes from the left hand the plate of the left hand tube to the upper terminal. So now we have a direct connection between the plate and the screen. And as we did above, we run it through the 470 ohm screen resistors. Why do we do that? Why do we have to put in screen resistors for triode operation? Well, look closely. What is between a short circuit in the screen and total annihilation of your high voltage winding if a short occurs? When you're in triode mode, you're receiving full plate voltage directly from the output transformer into your screen grid. Now, that would jeopardize both the output transformer and the power transformer if you developed a short. So screen resistors are absolutely essential if you're going to install a triode Pentode switch to protect your power transformer and output transformer against screen shorts. Okay, and the only reason they were included in the upper diagram for Pentode is that they have to be wired in for triode, and so they have to stay in place for the Pentode. So that's why you saw screen resistors in the Princeton Reverb circuit, and you normally don't. Why they were necessary with a Pentode triode switch, and why they are no longer necessary because we are removing that switch and restoring the circuit to original. One last comment before we move on. If you do a Pentode triode switch modification and you do add the screen resistors, be sure you don't add 5-watt screen resistors. If they're supposed to be sacrificial, they should be 1 watt. Okay, so just a word of the wise, don't use high wattage resistors in a sacrificial position. So now let's get started. All of the wiring for this has been done with this strange transparent insulation wire. So I'm going to go in and remove the toggle switch and all of the extraneous wiring that's been added to the circuit. Okay, here I've removed the switch, all the wires and the screen resistors, and positioned them pretty much as they were in the circuit and how they correspond to my drawing. So everything's out. It's came out nice and clean, and now without any harm to the chassis we can install a single throw, single pole toggle switch here and use it for our NFB circuit. Now I've quit fooling around with really cheap toggle switches, the kinds you can get like a bag full for $2, and I've been paying a little more for the Carling switches. Are just a whole lot better quality, but this is the one, single pole, single throw, that I'm going to install in the chassis, and this is the simplest of all switches. It's either on or off. It's like your wall switches at home for your lighting. Okay, so let's I'm going to set the camera down and install this jewel. So now we've removed that very obtrusive NFB switch and replaced it with the proper auxiliary AC receptacle. We've also removed the Pentode triode switch and replaced it with a proper ground switch, which we will use for switchable NFB loop. But once I remove these labels, now our control panel looks as it did when it came from the factory.
All right, I just wired the NFB switch using the period correct yellow cloth covered wire. One of the leads comes down right here to the external speaker jack, and the other runs down and connects right here to the end of that resistor on the eyelet board. And using the proper wires, you can see it's absolutely undetectable. It's just invisible. I haven't wired the primary circuit yet with the heavier power cord that the customer requested, but I can't resist pulling out all these electrolytic filter caps and replacing them with the cans. So let's do that now. Well, the 2 terminal strips and the 4 electrolytics came out with a couple nuts and bolts. We have to punch out this plug and mourn the fact that 2 holes were drilled in the chassis to install these terminal strips. That's a real shame. Okay, let's turn it over and see how it looks from the top. Yeah, that really looks hideous. They don't line up with anything. They're just very, very annoying to look at. I guess I have to punch out the plug and give some thought to some way to patch these holes to make them a little less disgusting in appearance. Okay, the plug's punched out, leaving room now for the can cap to be installed. Also, noticed that there were some notes that the tech wrote here on the chassis with a felt tip marker that aren't original and really don't look right at all. So I'm going to get a Q-tip and some lacquer thinner and get rid of those. Okay, that's all cleaned off. Looks a lot better. All right, now let's install that can cap and start wiring it. Okay, the can cap has been inserted in that hole in the chassis. Now we're going to fold the 4 prongs over and solder these 2 to both ground the can and also secure the can to the chassis. Looking at our power rail, we see that we have a 20K resistor on the B plus line up to the center tap of the primary of the output transformer. We go through 1K and we have another 20 microfarad, 18K, 20 microfarad, 18K, 20 microfarads. Here's our center tap, 20 microfarads through 1K, 20 microfarads through 18K, 20 microfarads, and then through 18K, 20 microfarads. So it appears to me that it's wired in properly. About the only thing left we have to tend to is the negative DC bias supply. Probably replace this cap because it doesn't look like it's an appropriate value, and check the resistors. And then be time to install the heavier gauge power cord that the customer sent with the amp. The much heavier gauge 3-wire power cord has been installed through a very, very stout strain relief. The green grounding wire has been soldered to a ground lug on the chassis. The white return wire has been soldered over here to the silver screw on the replacement AC receptacle, and then to that same terminal on the receptacle I've soldered one of the 2 primary wires for the power transformer. The black wire has gone to the gold screw on the AC receptacle, and then from there a wire has carried the positive, and from there a wire carries the AC down here to the on-off switch, from the on-off switch to the tail of the fuse holder, then from the outer lug on the fuse holder to the other primary wire for the power transformer. As I pan the entire circuit, and it looks really like it's pretty well back to original, that Carling switch, no matter how wonderful it may be, just glares in my face. So I looked through all of my spare parts drawers and I found a really nice Bakelite bodied single pole, single throw toggle switch. and I've tested it over and over again, and it seems to work perfectly. So I'm going to install this instead so that it will look right at home in the chassis and not stand out like that, albeit fabulous Carling switch, but it just attracts too much attention. There, now tell me that doesn't look a whole lot better. It's about the same color, same general shape as the power switch, and I think it fits right in now. I look at this, nothing jumps out at me as being incorrect. Well, the wiring's just about finished. I did replace that large electrolytic cap in the negative DC bias supply with an appropriate 50 microfarad at 50 volt. Now, one other thing here, as I look down the knobs, I just noticed this. One of these just sticks out as being in hideous condition. I'm just going to take a second here, remove this, and see if I can't clean it up. Well, how about that? A little Windex and a toothbrush and then some Armor All, and it puts the other knobs to shame now. So let's install it and see what our next repair task will be. I wanted to introduce the latest addition to our menagerie. This is Mitzi. She's about a 4 or 5 month old little female kitty. Showed up in our backyard, covered in mud and absolutely just starving to death. Kind of like Casey did a few years ago. And we've been feeding her. We trapped her and took her to the vet and had her fixed. So there's no more issues with her having kitties. And we're sort of feeding her and getting her back to her old fat and lovable self. Also, she's becoming very tame. Once she finishes eating, I'll try to get her to cooperate. And you'll see that she just loves, she's very affectionate. I find a lot of these female cats are, the males not so much. But she, I think, is going to be a really nice addition to the family. Whether she lives inside or not, I'm not sure. Ollie's kind of jealous of her garage. But I'll keep you posted, okay? And also, like I said, I'll try to get a video of her being affectionate and lovable. All right, it's test time in the old workshop. I have the tube set and unpacked and installed with the GZ34 rectifier. We have the Eurotubes probes safely ensconced in series beneath the 6v6 output tubes. The amp is plugged into the current limiter to prevent any internal short circuits from harming any components. I am piping in a 200 cycle per second tone with the signal generator. Okay, so let's flip the power switch on and let it warm up a bit, and then we'll see what kind of status and bias and a tone we get from this jewel. Well, let's check our bias first, and we see that the tubes are not terribly well matched, but we have about 9.5 watts of plate dissipation. Now we know that 70% of 12 watts, which should be the max for a vintage 6v6s like this, would be around 8.4 watts. So it's running a little hot, okay, especially this tube. Okay, we're looking here at close to 12 watts. That's just too much. So let's come up with a good way to reduce the bias and preserve the tone and the life expectancy of our 6v6s. Also, while we're at it, let's see if the amp is amping. Okay, we'll turn up the volume. We can hear that tolerable 200 cycle per second tone. Turn up the treble, we get some increase. We'll test the tone controls in just a second using our signal generator. The bass, ooh, that does. Bear in mind that 200 cycles per second is down in the bass frequency range, so the bass tone control has significant effect on the loudness of that 200 cycle per second tone. Now let's crank up the signal generator to a 2000 cycle per second tone, which will put it in the treble range. Okay, and let's, without deafening and nauseating all of the viewers, only a few of them, let's crank up the treble. You see how much louder it gets? Treble control is working just fine. Both of the tone controls and the volume control are dead quiet. Okay, let's switch back to a more taller and test our tremolo circuit. Let me crank up the volume here on our 200 cycle per second tone. And let's cruise on down the line here, crank up the intensity and speed. Well, great, I'm not hearing any tremolo effect. Now I know the owner requested that I slow the tremolo down, but hey, that's about as slow as it gets, okay? No trimming at all. So it looks like we're going to have to add that to our list of things to address. Okay, so let's go ahead and turn this jewel off and take a look at that tremolo circuit and see if we can't figure out what's wrong. Let's take a little break from today's repair marathon to check out some birthday gifts that I got from generous and thoughtful viewers. My birthday was in April, and I've been hanging on to these for a couple of weeks here so that I can include them in the video. First off, oh boy, it looks like we have a really snazzy black t-shirt. Let me unfold it and lay it out flat so you can check it out properly. Well, lo and behold, it's a really nice Fazio electric t-shirt from our good friend Colleen Fazio in Los Angeles, who's a really excellent amp tech who posts videos on YouTube. If you haven't checked out her YouTube channel, I advise that you do. I think you'll find it very interesting. Thanks so much, Colleen. Now let's see what the second gift is. This one is from Henry Gaulick in Ontario, Canada, who thought I might enjoy a Canadian license plate from my birth year. I do have a collection of plates. You might, I don't know if you can see them on the walls of the workshop from time to time, but I will very happily add this one to the collection. It's got a really nice patina and would look great on the wall. So thanks so much, Henry. You're very thoughtful, and Jack and Ollie and the gang really appreciate your generosity. Thanks so much from all of us. Now our next step is going to be to try to figure out why the tremolo doesn't work. And I was poking around in here and I found that one of the oscillation capacitors is not connected to the eyelet board. Okay, this .02 has broken loose on one end. Now there's no stub there or anything that I can solder to, so I'm going to have to replace this capacitor and see if we can get our oscillation loop to work again. Well, I replaced that damaged .02 microfarad disc capacitor with a brand new orange drop, and I think you'll hear that the tremolo now works just fine. Now to slow it down, we're going to increase the capacitance of one of the discs. And the way I'm going to do that is to add in parallel a .01 microfarad cap to this disc right here. I picked that one simply because it's closer and a little easier to get to. Now when I come down here and I'm going to connect the clip to the end of the parallel .01, listen to the speed of the tremolo. Hear the difference? It's slowed way down. So I'm going now to wire in this parallel capacitor, and I think our tremolo will be nice and slow and swampy. That's the slowest point. And we can speed it up. and you can hear the difference. Hear how it speeds up without that parallel cap. So that's the next step. Now, just to be a little less conspicuous, instead of that bright yellow 0.01 microfarad cap, I found a vintage disc 0.01 and put it in right beside, like a little stack of horizontal pancakes here. Okay, so let's see how that works. How swampy is that? Slow. I think that gives a great, very usable range for the tremolo. You know, I haven't done a good old-fashioned electronics analogy in a long while, and I thought maybe this would be a perfect time to take a little break from our repair video, and using springs to represent capacitors, let's see if we can understand why the oscillation loop slowed down when we added additional capacitance to one of the three loop capacitors. Now, for my analogy, I'm going to use springs. Now, springs can store up mechanical energy and release it. Okay, this is very similar to capacitors in the way they store up electrical energy and release it. So we have the difference of these will be mechanical, whereas capacitors are electrical, but the storing and release of energy principle will be the same. Now, I have on the left here a very small short spring, and it's going to represent a capacitor of low value, let's say 0.001 microfarads. And on the right, we'll have a capacitor of a much higher capacitance value. We'll say it is a 0.1 microfarad cap. Now, we know that capacitors charge and discharge. They will charge up and store energy and then release the energy. Okay, same with the larger capacitor. I'm trying to keep this from taking off across the room. Okay, but there's something pretty obvious here, and that is this one can store and discharge much more rapidly than the larger capacitor. Okay, now that difference, when we talk about capacitors, is the time constant of the capacitor. So the small one can store and discharge very rapidly. The large one, slow, quick, slow, quick. Now, do you see why adding additional capacitance in my oscillation loop slowed down the time constant of the two capacitors combined together, and therefore slowed down the speed of oscillation in the loop? Okay, it went from relatively high speed, which we thought was actually too high, to a slower speed. Thus, our oscillation loop was slowed down due to the increase in the time constant of one of the three oscillation loop capacitors. One topic that can be a little confusing is that some tremolo circuits require that a foot switch be plugged in for the tremolo to work. Others, like the Princeton Reverb that we're working on here now, do not require a foot switch to be plugged in. Now, why and how can you tell the difference in the two types of amps, those that need it and those that don't? Number one, the lower wattage amps like the VibroChamp and Princeton do not require the foot switch because the oscillation circuit is complete without it. Okay, so you can plug in the foot switch if you want to remotely turn the tremolo on and off, but you do not need it. With the higher wattage amps like the Deluxe Reverb and the higher wattage up to like 100 or more watts, all require a foot switch. Why? Because the foot switch
provides ground and is part of the oscillation circuit. These higher wattage amps also require the opto isolator because they are signal modulating rather than bias modulating. So if you have a relatively low wattage Princeton, the foot switch is optional, but if you have a Deluxe reverb or higher wattage amp with the opto isolator type of tremolo, then you do need a foot switch because it is part of the oscillation loop circuit. Now let's address the tube bias and the mismatch between the tubes. I think step one should be getting a balanced pair of 6v6s. These are the readings that I took, and you can see that the left one is a little high. It should be around 8 watts. The right one is way too high. So I went to my secret Al Capone's vault of tubes and brought a few of my vintage tubes out, and we're going to play a little mix and match here to see if we can find a much closer matched pair. Now, since the original left-hand tube was an RCA, I got another vintage RCA tube out of my stash which resembles the original right tube, and already I'm kind of stunned at the results. Look at the plate current now of what was originally the low tube, originally the 21.4 milliamps. It's almost doubled. And look at what happened to the former current hog, which was 27.6. It's way down. So let's turn this off because this isn't a real healthy situation here at around 16 watts. And look for another strong tube to replace the right hand. I think what we have here is the amp came with two very weak tubes. Okay, so I'm going to look for another strong one over here to replace the right hand tube with, and hopefully get a better match between the two. Okay, and now I plugged in another vintage RCA tube on the right, so we have two RCAs. These are my personal stash tubes here, and here are the original tubes. Let's see what kind of balance we get now. Well, and as you can see, we have a much better match with my two tubes. We're looking at around 34 milliamps and 37 milliamps. Let me do the calculations on this real quick and get the plate dissipation values. I know they're still way too high, but let's see what kind of percentage of difference we have. I did the math on the replacement pair of vintage tubes and got 12.8 watts and 14.2 watts. Mean is 13.5, difference is 1.4. That's a 10% difference between the two tubes, and that is most likely acceptable because the original pair had a difference of 25.3%. So I think this pair of RCA tubes is way better than the pair that up here that came with it. So I'm going to install my pair of vintage tubes. Now though, we have the problem of the bias being way too hot. Okay, plate dissipation should be around 8.4 maximum watts, and look at this, 50% too high, and this one's getting up to almost 100% too high, okay, say about 80% too high. So as you can see, way too hot. So next we're going to address the adjustment of bias. Well, I've got the chassis safely mounted in my mighty Mojo Tone chassis stand, and right off the bat I can see what's wrong with the bias circuit. There it is down there. Let's take a look at how it should look. Okay, we should have a 27K resistor taking some of our negative DC bias to ground and sending just the right amount up here to apply a negative DC bias to our grids. But lo and behold, and we have the 27K ohm resistor there, we have the smoothing cap here, we see that from this eyelet to here we'll be going to the intensity pot of the tremolo, But what do I see right here? Looks like a 100K resistor to ground. Well, that's not supposed to be there. Okay, that's going to reduce your negative DC bias voltage and up your plate current quite a bit. Okay, so this I think was tacked in here to try to up the bias of those weak old 6V6s. Now we don't need it. Let's remove this add-on 100K resistor and double check our bias and see if it's down around a normal level. Okay, that 100K resistor has been removed, and I've turned on the amp, and let's let the tubes warm up and we'll see what our hopefully lower plate dissipation is. Well, there you see it, and what a difference. It's gone way down. We're looking at what, 10 watts here? 25 milliamps times 400 volts. So yes, it's still a little bit high. This one's going to be 11.2, something like that. Still a little high, but nothing like 12.8 and 14.2. So let's test the resistance of our bias resistor, see if it's really 27K, and it would probably be a good idea maybe to increase that resistance a bit so that we can send more of our negative DC bias supply to the grids of our 6V6s and suppress that plate current a bit. I tried something a little different. Rather than altering the value of the 27K negative DC bias resistor, I've tried some different tubes, and I've ended up with, I think, a pair that are very close together and also yield a very usable plate dissipation. So let's write down these values, calculate the plate dissipation, and see if we don't have a winning pair of 6V6s. And here are those readings, milliamps, plate volts, and the left-hand tube now has a plate dissipation of 9 watts. Right tube is 8.3 watts. I think that's going to be just fine in this particular circuit. So I think our biasing and tube balancing is finished. Now, the one function of the amp we have not tested is the reverb. And remember, the reverb tank was not sent with it because it was working well. Well, fortunately, I have a brand new and appropriate reverb tank for this circuit. So I'm going to hook it up and let's double check to be sure that the reverb works. Because remember, the tremolo was supposed to work also, and it didn't, probably due to some sort of damage in shipment. But let's double check. Okay, let me get this out, hook it up, and we'll see if the reverb works. All right, I've got the reverb connected with shielded cables. It's just laying out here on the bench. I've got the amp turned on, and the reverb controls are both at about half position. So let's see what we get when we bounce the tank. Definitely we have reverb. So we'll be able to include reverb then in our audio testing. And I'm really glad, because that's one of my favorite parts of any reverb amp, is that sound that we all love, us hounds. And now for the final repair, hopefully. Remember, the pilot light was burned out. I just put in a new number 47 bulb, and we see that it works beautifully. Okay, I think we're ready to start doing some audio testing on this jewel. Before we start our audio testing, I've got a little secret to let you in on. In every previous view of this circuit, I had these screen resistors installed on the 6V6 tube sockets. Okay, now I have removed them. As we saw in my explanation, they're not necessary. But let's see how many people spot them in an early view and run to the comments section to criticize or kind of nitpick over the presence of those screen resistors. Okay, instead of watching the whole video to see how everything's resolved.
Okay, it's sort of like a little lesson here, and it's also our little secret. Okay, so don't tell anyone. Well, I guess we're about ready for our audio demo of the Blackface Princeton Reverb amp. We have our SM57 microphone aimed just off the center of the cone of our 12-inch Jensen speaker. We've got Ollie and Jack all tuned up and ready to go. So without further ado, let's begin our audio demonstration. Well, I guess that's about it for this video on the Pre-CBS Fender Princeton Reverb amp. I hope you enjoyed it. I threw in about 5 digressions within the video where I went into much greater detail on certain features that were brought up, topics that arose during the video. I hope that that didn't upset the progression of the video too much, and I hope that the information was informative and helpful to you. Okay, let me know in the comment section. Meanwhile, I want to thank all my PayPal contributors and Patreon patrons for their continued support of our channel. We really appreciate it. Should you like to join them in supporting our channel, I will put some links in the video description to enable you to do so. I also want to thank those generous viewers who sent us the fabulous gifts that we opened during the video, and just tell you that for all you viewers, just how important you are to us and how much we appreciate your time and interest that you spend watching our videos. With that in mind, thanks again for joining us, and please stay tuned for future postings, which should be in the very near future. Until then, bye for now.